Hey guys, so from today I'll be starting on with a new playlist that is on acid properties. Acid we all know, atomicity, consistency, isolation and durability. We have all learned that in ACADS, but 99% of the people would be knowing what acid is, but when we ask the next step like, hey, can you tell me in depth how acid works? So 99% won't be able to tell that, and that is the sole purpose I'm trying to solve with this new series. I would be discussing in depth how atomicity actually works, how consistency, isolation, durability is actually achieved at a core, at a database level. So let's start. So first we'll go through the agenda. So before starting with acid properties, the very much important thing that you guys need to understand is like how actually write happens in the database level. If you are not knowing, if you are firing any query or transaction statement, if you are firing how exactly it happens, then you won't be able to understand how exactly acid works. So this is the something which is a base thing that you guys should be knowing, and that's the reason I would be just touch basing on it at a very high level, so that like you should be having a framework like, hey, this is how the entry is saved in the database. Suppose that is clear, then we would be discussing on an acid. So atomicity, what is the definition and example and how internally it works. Consistency, the definition, example and how internally works. Isolation, definition, example. Again, there are multiple read-write issues that is attached with isolation, and then the different isolation levels. And then finally durability, definition, example and how internally it works. So for every single section of acid properties there would be a separate video. So let's start with the very first thing, how write happens in SQL DB. So whenever let's say you are firing a transaction, update, insert, delete, these are all different kind of transition statements, mutation statements that we generally fire at a database level. Now the important thing is how those are internally getting executed and how your data is getting manipulated. So now how the transaction starts. So whenever you fire a transaction, then first you require a data. So let's say you are updating a record. So for updating that record should be first present in the memory, because no one can directly perform an operation at a disk level. It has to be in memory. So first that record is pulled into in memory. Now the update instruction is executed. So let's say you want to update an account balance. Update account, set balance equal to 500 rupees, where account ID is equal to 123. Let's say this kind of an instruction that you want to fire. What it happens is like first account, for that account ID 123, that row is pulled it into in memory. Now the account balance is updated in memory. So initially let's say the account balance was 200. Now it is getting set to 500, not yet on the disk. Now a corresponding val or undo redo file is created and store it in the in memory. Now similarly inside your one transaction there can be multiple such instructions. So all those instructions manipulate or mutate the data in memory. Parallelly they write those instructions in the val file, and those instructions are at certain interval of time are flushed onto the disk. Now finally when you fire the commit command, then fsync, it is a instruction at an OS level. That fsync command is executed and the val file, the commit instructions is pushed onto the disk. Now the question is why we need a val file. You are updating the data in the in memory. Why? Because it is faster obviously. Then we want a durability of a data. We do not want the data to be lost. So that's the reason write ahead log file, which is an append only mode. Writing that in the file is very fast, and again that is written in memory, and parallelly it is flushed onto the disk. So you might be thinking, hey, if you want to write it on the disk, then why we can't directly write the instructions on the disk? Why we need a val file? Because it is an append only file. There is no data structure, nothing, just append instructions one after the another. That is much faster than searching a particular location on your disk and writing it over there. It is not feasible. That's the reason we use a val file, and then post that val file is burnt onto the disk. Now what happens is like as soon as the val file is there on the disk, means all of the data that you want, even if it is not there in your table, in your disk, in your particular block, in your particular page, but it is present inside the val file, and that val file is on the disk. We are ensured like, okay, even if something crash happens, something happens, my data is there on the disk, not in the format of tables or stuff like that, but it is in the format of the val file. So now we give a commit instructions to the user stating like, hey, your data has been successfully persisted on the disk. And now what happens is like at a background, at an async level, what database engine does is like it reads the val file, it reads the database entry, it compares like, okay, my database entry is stale as compared to the val file. It takes that val file information and updates it. This happens asynchronously. User is not aware about that part. User just knows like, okay, hey, my data is preserved, database has given me a success message, that's it. How internally database works, this is how it works. This is what I have explained you. This was very much important for you to understand how exactly a write happens in the database. This is going to set your base, and this would help you to understand how exactly atomicity, consistency, isolation and durability, how that is achieved internally. If you are not aware like how actually write happens in the database level, then internal working of these concepts might bounce over your head. I hope you have understood this thing. Let's start with next section. This won't be taking too much of the time. So as said, we know atomicity, consistency, isolation, durability, we all know in the ACAD. So I just won't be taking too much of a time on this particular slide. Let's start deep diving into every single component. So starting with atomicity. The basic principle of atomicity we all know. Either all the instructions are completed or nothing is completed. Assume this is an account ID. Account ID ACC123. Now there is a balance 500 rupees in that account. This is how, let's say, a transaction is getting created. Just take it as a hypothetical example. You want to perform two operations. Update balance with 100 rupees and deduct balance minus 50 rupees. So there is this one transaction, and in this one transaction multiple instructions are there. What atomicity means? All the statements in this particular transaction should get executed. Either or none should get executed. Let's say these are the two instructions in the transaction. So either both should get executed or none should get executed. What should be the expected output assuming this transaction is successfully executed or not? If this transaction is not successfully executed, let's say there is an error occurred when we are executing this particular statement or this particular statement. So my original balance was 500 rupees. My updated balance should be 500 rupees only. If this transaction is executed successfully, then here from 500 we are adding it to 600, and then here we are deducting from 600, that is 550, and finally it should be 550. If it is successfully executed, my balance should be 550. If something error happens, it should be rolled back automatically and my balance should be 500 rupees. How atomicity works? The important thing is there can be multiple use cases. Commit is successful. Crash after commit happens and crash before commit. So these both the instructions are executed successfully. Now you have committed. Committed, again recall how exactly the write happens in the database. So commit instruction is fired. That commit is updated in the val and that is burnt onto the disk. So now inside your val file on the disk, this commit instruction is also present. And then finally, let's say error happened during these update instructions. Let's go through every single use case one by one to understand how exactly atomicity works internally, how exactly database ensures like either all the instructions should be executed or none should be executed. Let's start with first use case, commit success. This is the same example that we would be taking and seeing how exactly atomicity works. So remember the important thing that I've mentioned, val file is something which is used for ensuring your database entries are present in the database. Similarly, val files are used for ensuring the atomicity. Let's go step by step. So begin transaction has happened. Fetch account balance. Whenever you fetch something, val file is not created. Updating account balance. The transaction has begun. This is TID. This is not generally TID. This is XID. But just for understanding purpose, I have taken it as a TID. Update accounts. New values. Account ID. Account 123. Balance is equal to 600. Initially it was 500. Old value is equal to 500. We are updating it to 600. This is the first update instruction that is present. There is a LSN number that is attached to every single set of instructions. What happens is you are updating the account balance by deducting 50 rupees. Account ID 123, update new value. Again, this is an account table. Balance is going to be 550. So this is this instruction and this is this instruction. Finally, the commit thing. So this is the commit instruction, LSN4 commit. This val file, all the 4 instructions are present and this is in memory. But one thing you need to understand is like not all the instructions are present and then only after commit the val file is burnt onto the disk. No, it is not like that. There is a frequency, there is a configuration. Assume that is a kind of a timer or a scheduler. So after that particular time or schedule, whatever information is present in the val file, that is moved to the disk. So this is how the val file is written. Now assume all these things are completed and now your val file is present onto the disk. Val is fsynced to the disk to LSN4 before reporting commit success to the user. Once the val file commit instruction is updated onto the disk, then only we are saying commit success to the user. Data page in the disk is updated parallelly at the background. Here use case that we are trying to discuss is, this is a happy path. Your transaction is executed successfully, your commit is done, it is updated into the val file and parallelly the data is updated into the disk. So initially in your data page the value was 500. Now the value in your data page is 550 and post that let's say crash happens, it doesn't matter because now your database is having a new value. Let's say after a recovery, after 1 hour, if user is coming and user is seeing, he would be able to find 550. Why? Because now your database is having an updated value. Let's say discuss on the use case 2. Crash after commit is successful. Again same example we would be taking. Let's follow this val file. So transaction started. Transaction ID 7001. Update account. We have updated the account balance to 600. Then LSN3. We have updated this 550 here and 600 here. So now both the things has happened. Commit. We have updated. Flush onto the disk up to LSN4 before reporting success to the user. Okay. Now commit is sent to the user. But what is the difference between previous use case and this use case? The difference between both is in there data page was asynchronously updated. So your database was having an updated value 550. In this case, just your commit is sent, the val file is sent to the disk. but your data page is not yet updated. So your data page is still having the old value of 500, but your val file on disk is having 550. And before updating that onto the database, the crash happens. So data on the disk has old value 500, that is LSN1. Now what happens? Okay, my database restarts and then there is a recovery that happens. So once the recovery starts, what database engine does is it reads the val file from the disk and compare. Assume this case, LSN -1 equal to 500 on disk. LSN 4 is equal to 550. It is present in val file on disk. So now what it does is it compares the LSN. My LSN is old than what is present in the val file, plus it looks like okay whether this val file L4 instruction it is having a commit. So if I am outdated, then this LSN plus it has a commit instructions means there was something that was supposed to be updated into the database but I got crashed. So now it is my responsibility to update that. That's the reason data page is now updated. So now data page in the disk is updated because LSN -1 is less than 4 and TID 7001 has a commit message. So balance is now updated to 550. So you see, this is how the recovery happens. Whenever we are sending a commit success to the user and after that the crash happens, we might be wondering as a normal user like, hey, how my database value got updated, but this is how it happens internally. Now we would be looking into the third use case, crash before commit. So again, same examples I would be taking. The val file again it is going to be the same. What is the difference now? Here in this use case, the difference is it is not flushed onto the disk. These instructions, let's say these might be there on the disk because as I mentioned, periodically the updation happens on the disk. But LSN4 commit, it was there in memory, but not on the disk. So it was not flushed onto the disk. So val is fsynced to the disk up to LSN3. Crash happened. Data on the disk has old value that is 500, that is LSN -1. Again the database restart, it would enter into the recovery mode, read the val file from the disk and compare. So now again it is comparing. Data page in the disk is updated, is not updated, sorry. Data page in disk is not updated, sorry, this is a typo, because LSN -1 is less than LSN3. This condition is satisfied, but TID 701 has no commit. So this is a important thing. It has to ensure like the data is committed. If there is no commit instructions for that particular val file, then it is not going to update the data, and that's the reason now my old data is 500. My database is still preserved, my database is still having a old value. Even if these both update instructions are executed, my database is still having the old value. Why? Because these both were executed in the val file onto the disk but not updated on the data page. Before that the crash happened, and when I was in the recovery mode, I observed like hey, my LSN value is older than what is there onto the disk. That is perfectly fine. It means I should update, but the second condition is whether there is a commit instruction. If the commit instruction was also burnt, means okay fine, now I should update it, similar to my use case 2. But now because I am not finding the commit instructions, I would be rollbacking or I would be just keeping my old data, that is 500. Cool. Now finally we would be looking into the last use case, that is error in last update statement. So you see this thing, same example. What we are trying to discuss here is like this was updated onto the disk, but not, when I am saying onto the disk, it means the instruction in the val file is present onto the disk. It has not yet been updated onto the data page. But now when I was executing this, it got failed because of some error. And abort happened. So val is synced to the disk up to LSN3. Till now we were burning commit, now we are burning abort statement. Database engine, it reads the val from the disk, it finds the abort message in the val file. So obviously when there was an abort message, all these instructions, nothing is going to get executed because there was an abort message. And so now my in memory is also having a old value 500 and my database is also having a old value 500. I hope so with this particular video you are able to understand how Atomicity works internally. Always there has been a confusion. We know Atomicity, either all the statements are executed or no statement is getting executed, but at a database level it was very much important as a system designer, as an engineer, for us to understand how exactly database works. If you feel I have added some valuable knowledge, so please do consider liking this particular video, subscribing to my channel and commenting something if you feel I have accidentally said something wrong or some improvement is needed. In the next video we would be discussing on the consistency part. Thanks.